Here in Chapter 8, we're going to be learning about systems of equations. Systems of equations basically means you've got more than one equation that has to be solved all at the same time. So if you've got equation A and equation B, whatever you've got that you think is a solution, it has to solve equation A and it also has to solve equation B. The best way to describe that would be you're talking about a situation in which there are two different requirements. Like in this problem here. There's one requirement that talks about what happens when you add the numbers, and then there's a second requirement that talks about what happens when you subtract the numbers. So, if we're going to call the two numbers x and y, then when you add them, x plus y has to add up to 35, but when you subtract them, x minus y has to equal 11. That type of thing, that's what we mean when we say a system of equations. The system part, that word means there's more than one and they both have to work at the same time. So, now, how do we solve these things? Well, there's more than one technique, and that's one of the interesting things about Chapter 8. We're going to learn one technique here in 8.1, we're going to learn another technique in 8.2, and so on. So, the basic idea that underlies all of those techniques is that when you look at things like this, these things have graphs. And if you graph them, the picture's going to tell you something that the equations might not tell you. And that's actually one of the reasons why we learn graphing at all, because the picture conveys information a different way and maybe a more useful way. So if you were to graph these, x plus y equals 35 is going to be a line looking roughly like that. It'll have an x-intercept at 35 and a y-intercept at 35. And x minus y equals 11 will be an equation looking about like that. It'll have an x-intercept at 11 and a y-intercept at negative 11. But when you look at these two lines, there's something happening there that should be pretty obvious and pretty important. The two lines are intersecting with each other. And the solution that you're looking for has to be something that solves both equations. In other words, visually speaking, that means we're looking for a point where the point is on both lines. So, when we say this, what are the two numbers? Translate that into find a point on both lines. And you look at the picture, and it's kind of obvious. It's that point right there. That point is on both lines. So there's going to be some sort of x-coordinate and some sort of y-coordinate, and that's kind of the hard part of the problem. It's easy to see that there's an intersection, but saying what that intersection actually is kind of tricky. In this case, it comes out to be 23 and 12, but what that actually means is the two numbers, remember it's a word problem, the two numbers are 23 and 12. And this technique is something we're going to call the graphing technique. And it's our most rudimentary, most basic sort of starting technique. We'll come up with a better technique in section 8.2. But for right now, just as a basic idea, let's consider in general, if you've got two graphs, two lines that you've graphed, what kinds of things can happen? And there's really only three things that can happen. If you draw two lines, most of the time, if you just draw two random lines going in two random directions, they will probably intersect somewhere. But it is possible that when you draw two lines, they might, just by accident, be perfectly parallel to each other, like the second picture here. And then there's a third thing that can happen, and this isn't really obvious until you realize you're not actually starting from the picture, you're starting from equations. So if you have equations that are like these ones here, notice that third picture. The equations there look like they're different equations, But when you actually graph the line that goes with those equations, you realize that, oh my gosh, they're both actually the same line. So although you might think you have two equations, they might really be two equations for the same line. So when you draw two lines, these are the only three things that can happen. They can either intersect, or they can be parallel, or they can be the same line. So there are really only three types of answers that you can get. In the first case, where the two lines intersect somewhere, the type of answer you're expecting is a point. It has some sort of coordinates. There's an x-coordinate, there's a y-coordinate. So usually, most of the time, the answers to a system of equations will be something comma something. On the other hand, if the two lines are parallel, and what you're supposed to be looking for is the point that is on both lines, the point where they intersect, if they're parallel, there is no point of intersection. So in that situation, you would say, no solution. And that's a perfectly acceptable answer. You can say that as an answer to one of these questions. If their lines are parallel, there's no solution. And then the third case is kind of the tricky one. When you see no solution as a possibility, your mind automatically remembers way back in our first chapter of Algebra 1, and you're thinking the other possibility would then have to be all real numbers. Because those are the two weird cases you had back in Algebra 1, was no solution versus all real numbers. But think about the words there, all real numbers. And think about that picture where you've got a duplicate line. The answers are not numbers, they're points, so that part's wrong. And not every point is a solution. I mean, there's plenty of points there that are not on either one of the lines, so all isn't right either. So we just don't say all real numbers. That's not the proper vocabulary for what's happening in this situation. We say something that sounds kind of similar, but is actually more accurate. What we say is infinitely many solutions. That's a correct description of what's happening there. And when you're writing things on tests, it's perfectly acceptable to abbreviate that and just say IMS. I know what that means. If you write that on your test, I'll give you full credit if that's the right answer. So those are the three cases of what can happen when you're solving a system of equations. There can be a point, there can be no solution, or there can be infinitely many solutions. So, one last little important part we got to cover is that this graphing method we have right now, it's great for understanding what can happen, but it's actually really terrible when you want the actual answer. And this is why we're going to have more to Chapter 8 than just this first section. So I'm going to do one more example to show you sort of the downside of this graphing method and help motivate you to want to take a look at 8.2 as soon as possible. So let's consider this problem here. We have two lines. We're going to graph each one of those lines, and we're going to try to figure out where the point of intersection is. So, step one, graph the two lines. You might want to pause the video, get out a piece of graph paper, and try graphing the lines. And then press play and I'll work it out. Alright, so for this first one here, to graph it, I'm going to do this one in blue. And I think I'll use the intercept method. It's not the only method. You can use whichever graphing method you prefer, but I kind of prefer the intercept method here. If I plug in 0 for x, y comes out -4. If I plug in 0 for y, x comes out 2. 2, 3, 4 is down there. 2, 0 is there. And then if you want to get an accurate answer, it's probably a good idea to get an actual ruler and draw this as carefully as you can, because if you're really sloppy and you draw a line like that, that's not going to help you find the right answer. So get yourself a ruler, draw these lines as straight as you can, because accuracy is going to help you find the answer. Okay, second line. I'm going to do this one in red. And this one's a little trickier to graph. I don't think the intercept method would work really well. The y-intercept is way down at -13, which is off the bottom of my picture. And the x-intercept is 13/5. That's a nightmare. So the other technique that you can use for graphing is to put the thing in mx plus b form and use the slope and the intercept. But even that's not particularly useful here, because that y-intercept way down at negative 13 is such a pain. So what I'm going to do is I'm going to go back to an even more rudimentary method, the table of values. I'm just going to plug in numbers until I get things that I can plot. Like plugging in 0 for x gives you negative 13 for y. That won't fit on my picture. 1 for x gives me negative 8 for y. That one might fit. And 2 for x gives me negative 3 for y. That'll definitely fit. So I can graph these points here, this one and this one. 1, negative 8. 2, 3, 4, 5, 6, 7, 8 is down there. 2, negative 3 is over there. And again, use a ruler, because if you try to eyeball it, who knows where you're going to end up. It won't be accurate enough to get the proper intersection. So you get a ruler, you connect those dots as well as you can, and you'll notice that if you're even a little bit inaccurate, like what I'm doing over here, then your point of intersection ends up really inaccurate. So you have to be super rigorously careful when you're drawing these things, and that's a problem. That's not something that's good to know about this graphing method. That's a little better. And then ultimately, because this is so dependent on how carefully you draw, the point of intersection you're getting is always just a little bit of guess. You're not 100% sure it's right from looking at the picture because you're not 100% confident of your picture. That looks like the point 3, 2. So I think the answer is 3, 2, but I'm not really confident of that unless I check it. And don't forget that you can check. To check an answer like this, you would go back to the original equation, and you would plug in 3 for x, and you would plug in 2 for y. Except there's 2 equations. You got to check both of them. So you got to plug into the second equation, x and y. And do they both work or not? If either one of them fails, your answer's wrong. They both have to work. In this case, they do both work. 5 times 3 is 15, minus 2 is 13. 2 times 3 is 6, minus 2 is 4. So it turns out that my picture was good enough to get the right answer. So when you look at doing that by hand, you should realize this graphing method, it helps you see what's going on. It's very useful for that, but it's not really useful when you want the actual exact answer. So please come back for section 8.2, where we'll talk about doing this without drawing pictures.